As for the others, at this moment, I just let you know, and you can check the taskbook, or maybe you can look up through the internet, and so that you can find the property. Well, if we want to have some other derivation, in fact, you can try these. And this one, this is the exact formula. All right. And the exact formula, then we will have the new term covariance. If we introduce new terms covariance here, how to have the calculation for covariance? We have a variable x sub I and variable x sub j, and this is a definition to have the calculation. Variable minus its mean, multiply another variable minus its mean, and we have the multiply the second term, and so that we have the calculation for expected value. And in fact, you can try, if we have that way, we will have the reduced result, the product form for the two variables minus the product form of the individual expected values. Well, this one, in fact, you can try, but I just want to let you know we can introduce covariance first. If we can introduce covariance first, then we will have the expression for this one. If we want to calculate variance, well, if I want to derive it, maybe not difficult, however, it's lengthy. Because of lengthy derivation, so I let you know we have these. So you can try. Or maybe you can look up, or maybe you can use Google to find the result, or find the procedure to have the derivation. Well, as for covariance, actually, we have this result. And later I may show you the definition for this one, maybe a bit simpler. So I use this one to have some further derivation. Well, actually, if we have the given formula here, we will have the results. Look at this. If random variables are independent, here actually we will have the property independent imply we have covariance here. However, covariance equal to 0 imply independence? No. Well, we just want to apply the property. As for this one, you can look up for sure. If we have random variables, independent random variables, so right now we can have 0 covariance. To have 0 covariance, just follow the equation here. So you will have 0. If you have 0, then these terms vanish. These terms vanish, so you will have the formula here. All right. So we just know if we have independence, then we can imply 0 covariance. So 0 covariance, then you have 0 for the maybe the second term for this equation. Therefore, we have the reduced equation. All right. So this page, maybe I skip some derivation. Here, this one, you can check it, how to have it. But I try to let you know the covariance, how to have the simplified expression for covariance here. Well, this one, just follow the definition. So we will have these. Well, again, I assume we have continuous random variables. So assume xi and xj are continuous random variable. All right, so then we can have further integral. Well, if so, we have I, J. Right? Well, if so, then we have an integral, but we try to expand. But here I have a simplified expression. I just have a double integral, and here expression, so ij minus j this, minus I j and minus well, for this one, this is a expansion for the term here.
The last term should be constant, but the unit is not.
Finally, we have this ij. That's it. So the term here, I, J, all right, and I just expand, so I and J, and J, so J here, minus, and finally we have this one plus. All right, and still we have the join PDF. All right, so if so, then you can have the results like this. IJ, and I skip the PDF here. And minus this one. For this one, actually, it's a constant. So you will have a constant. I move to the outside. So this one, we have a J. And likewise, I skip this. And J move to outside. And you have I. And finally, it's a constant, so you can move it totally to the outside. Sorry, it's plus. Ij. And here you have, it's 1. All right, so if you can rewrite it so that we have a double integral for Ij and joint distribution. So this one actually it's Ij expected value. And this one likewise it's expected value J. So I and J. So we have the product for expected value Xi and product value of Xj. And this one is J, and this one is expected value I. All right, so second one, minus polyphone, and plus polyphone. So finally, we will have these. 2 minus plus 1, so of course, you will have a single one. That's it. All right, so just let you know, you can use continuous random variable to understand, yes, we can reach the reduced derivation covariance actually equal to this equation. And if you know this, in fact, you can use this way to derive variance in the previous discussion. Previous discussion, we will have the similar result. What kind of result? Let me move to this one to let you know. This one. So you can follow the previous idea so that you can have a derivation for this kind of derivation. You see, we have an index I and j, and you can think I and j, they are the same. So finally, of course, you should have this equation, right? So let me jump to this one. So I don't know the derivation for covariance. You can use the similar procedure. Right now, we have two random variables, but in the previous one, you just have a single one, so it's really simple. It won't be necessary to have the joint distribution. You just have a distribution for that variable. However, the procedure, they are similar. So that's why I think if you understand the current derivation, you will understand that one. So that we have covariance here. And likewise, we will have the result. I rewrite results for variance. Well, I still use the blue color. Variance. Variance x. Actually, it will be x squared minus square of expected value. Right now, assume you can set I equal to j. Right? You can think about I equal to j, and the I equal to j, the definition here should be variance. And so that if we have I equal to j, so it will be square. It will be square of the expected value. Well, that's also, I just don't know if you want to have the derivation, you can try continuous random variable. Likewise, you can use discrete random variable to illustrate the results like this. All right, so this is the derivation for this equation. Well, I still want to know if you want to derive the results here. Be patient, and so that you will understand how to have the expression by using the newly introduced notation covariance. All right, that's all. So for the derivation here, to know the property, is it okay? If you still have some question, you can check the recorded video, and so that you can listen to the discussion again. All right, I assume you can understand some, maybe not all, but let me continue.